In this video, we're going to take a look at section 2.1 on frequency distributions. So let's start with a definition. A frequency distribution is a table in which the data is divided into groups, which we call classes, and the number of data that occurs in each group is given. This number is called the frequency for that particular class. All right, so it's a table with two columns. The first column being the groups. We define those in the first column, and there's some rules about how those can be defined. And then in the second column, we have the frequencies, how many data values occur in each of those groups. So it's just a matter of counting, grouping, and then counting how many are in that group. Why would we want to go through such an exercise? So I want to illustrate by example. So here we have a set of data that I got from the internet. In fact, the source for this is down here. It's just off the screen, but it's right here. Right? So it's from Kaggle. And I thought maybe this might be of interest to some students. This is the Critic review scores for Animal Crossing, and I'm assuming it's the newest one that just came out. This is 2020, and I'm aware that I don't play the game myself, but I'm pretty sure, unless I'm thinking of a different game, I'm pretty sure Animal Crossing just had a new release, and it seemed to be pretty popular, and these Critic scores seem to indicate that, at least with the critics, it's popular as well. I see a lot of 100s, for example. However, looking at a big set of data like this on a screen, in fact, there's 107. It might be hard to believe, but there's 107 review scores here. What does this data tell me? All right. So what I want to ask is, what do all these numbers mean? So when you just have a set of numbers, it's very difficult to extract any sort of meaning out of that. You might have some intuitions about, again, is it more towards the 100? You know, is the average more towards the 100, or is it more towards the lower end? Which, by the way, if you look, you can get that by looking at the set of data too. It looks like 70 is the lowest value. 100 is the highest value. There's a lot of 100s, but I can't be 100% sure. My intuition tells me this is a really popular game. A lot of critics like it, but just having this big set of numbers to look at, it's hard to extract a lot of meaning out of it. And so we want to process it in some way to be able to better understand what's going on with this set of data. And one way of processing it is to construct a frequency distribution. There are other things that we will be able to do with a set of data, and I may continue to use this set of data as we go through the next several chapters and apply different tools, different analyses to this set of data to illustrate different ways that we can kind of slice and dice it, I think is a common term among statisticians, to try to find some meaning out of it. All right. All right. So one way you might think of organizing this data is to maybe, since it's, these are whole numbers, and it goes from 70 as the lowest to 100 as the highest, you might think we could just kind of group them in terms of, the data values that are in the 70s, the data values that are in the 80s. I'm trying to think of a nice way to describe that way of dividing up the data by tens, I guess, maybe would be a good way to say it. And this is not a bad idea, really. And this actually is fairly valid. 70 to 79 would be our first group. 80 to 89 would be our second group. So this is really not a bad way to think of it. But instead of saying 70s, 80s, 90s, we want to be more formal about it. So this is a little bit too informal is what I want to say. All right. You could do something like this, 70 to 80, 80 to 90, 90 to 100. But there's a big issue with setting up our groups in this way. So can you think of why this actually is a problem? So let me ask you a question. What if we have a review score that's exactly 80? In fact, I think we do, right? So if we go back to the set of data, can I find one in here? Yes, like there's several, 80, 80, 80, right? So what do I do with that particular data value? Which group do I count it in? 80 is mentioned in the first group, so I would need to count it in this group. but 80 is also mentioned in the second group, so I'd have to count it here. And so the issue with setting it up like this is that you have an overlap here. And so if a data value occurs in that overlap, it's going to get double counted. So you need to be careful when you're setting up your groups, your classes, that that there's no overlap, that where one ends, the next one begins. And also you don't want to have any gaps. I didn't do an example of that, but you also wouldn't want to do something like, 70 to 77 and then 80 to 90, because what about 78? What if that occurs as a critic review score? There would be no place for it. So these groups have to be very carefully defined so that there's no cracks where data values could go missing because they don't get counted in any groups. And also you don't want to have any overlap because then you might have to count that data value twice. So you do need to be a little bit careful about how you set up these groups. Here's another example of a way that you might organize the data that is invalid. So what is the issue here with the way I've organized these groups? So the issue, I guess when I ask you a question like that, maybe pause the video, think about it, come up with an idea of an answer, and then resume the video to see what I have to say about it. You might think this would make sense because as we kind of saw in the data, it seemed to be more skewed. That's a statistical term, which means that, if you think of the normal case being a lot in the middle and not so many on the outsides, skewed means there's a lot in one direction or another, not in the middle, but it's more to the right or more to the left. For this particular set of data, it seems to be skewed more towards the 100s, right? It's skewed to the right. There's less values on the lower end. It seems to be there's more values on the higher end. And so you might think, well, a good way to organize our frequency distribution, since there's more data values on the upper end, is to maybe make the groups bigger on the lower end so that we get more numbers there, right? So maybe going 70 to 84, and we can, we get to count more numbers because it's a wider group. We're casting a bigger net there. Whereas here I have just 98 to 100, which is going to have a lot because we saw there's a lot of 100s in that set of data. And so this will also have a lot. And by making this group bigger, we'll get more numbers in there too. And so we just maybe try to even it out a little bit. You might think that's a good idea, but everything I just said is a bad idea. It's going to distort the distribution of the data. We want to have a realistic sense of how the data is distributed. And if it is skewed more to the 100s, we want to be able to see that in our data. And if we set up the groups so that we get an even number in each group, we don't get to see that skewness. We don't get to see it skewed to the right or to the left because we've set it up so that it looks like it's even all the way through. And so we don't want to have misleading data. We don't want to have, not that the data is misleading, but we don't want to have a misleading frequency distribution or any kind of tool that we use. We want to try to make it as objective as possible. We don't want to set it up in any way that would be misleading, right? And so this would be misleading because when somebody looks at the table, they're going to assume that these are of equal weight, but that's not the case. We've widened this group, we've narrowed this one, and that just is going to distort the picture of the distribution that we're going to get when we construct this frequency distribution. And so here is what I propose would be the best way of organizing our frequency distribution. So here, each class covers the same distance, if you will, right? So this goes from 61 to 70, that's a gap of 9. This goes from 71 to 80, that's also a gap of 9. So we're not going to distort our data by having a wider group for one and a narrower group for another. There's no gaps here. Now you might say, oh, wait, between 70 and 71, but if you look at our set of data, there's no values between 70 and 71. We are dealing with integers, with whole numbers. And so there's no decimal numbers that we have to worry about. Now, if we saw review scores of like 70.5, this would be a problem because 70.5 would fall in a gap. It'd fall in a crack here and would not get counted. And so we'd have to do 61 to 70.9 in order to make sure we got 70.5 counted in one of our groups. So if there's decimals in your data, you're going to need to have decimals in the way you define your groups. All right. And also there's no overlap, right? So it's not, if we have a review score of 70, there's not two places that it could get counted. There's only one place it can get counted. And so this is a well-defined frequency distribution. And we're going to, really pick apart all the structure of what we have here in just a minute. But what I would like to do, and I don't want to make you have to sit there and watch me, but I haven't done it yet myself, is let's take our set of data and fill in the right-hand side of this column. So maybe I'll give you a preview of what that process is like. It's very tedious, and it's very prone to making mistakes. So maybe you could also double check me to make sure that I'm getting the right numbers here by also counting for me. So, we'll go back to the set of data, maybe pause the video. And if you can see the numbers, help me count. And if I have it wrong, send me an email or leave a comment in the comment section. And maybe I'll have to go back and edit my video and, correct myself. But hopefully I'll do it carefully. And you want to be as organized as possible, as careful as possible when you're doing this. And like I said, it helps to have like sort of a buddy system where you and somebody else do it. And that way, if you don't agree, somebody's made a mistake and you can try to resolve it. All right, so let's go back to our set of data. So I have 61 through 70. Now that one's kind of a silly group to make, but I think that makes more sense because if we started at 70 and we went to like from 70 to 79, for example, which would be another way to go, that might make more sense for that group. You might get a few more data values in that group. But then when you got to the end of it, you'd have 90 to 99 because you have to keep the size of the groups the same. And then 100 would have to be in its own group. You'd have to have 100 to 109, which then that wouldn't make sense, right? Because you can't go over 100 anyways. And so it would just be an awkward class if we did it that way as well. So I guess you're going to have an awkward one either way. I decided to make the first one the awkward one. So we're going from 61 to 70. And if you look at this set of data, if I've looked at it carefully enough, there's only one value that goes in that group, which is 70. There are no values in the 60s essentially, but we do have this one here that is 70. So we have one. That's the frequency for that class. So I know I say group and I kind of use more informal language, but I'll try to slowly transition to just using the technical terms. So for this particular class, the frequency is 1. There's only one data value in that group. Now, this one's going to take a little more time, but maybe we'll do this one together, and then I'll pause the recording and do the other two so you don't have to sit there and watch me count all those numbers. But let's do 71 through 80 together. All right, so let's go back to this. So what I'm thinking to do, now, one way to approach this would be to order these numbers numerically. I think that'd probably make it a lot easier, but that's also going to take a long time because, like I said, there's 107 values here. I believe that's how many there was. And to write those in numerical order, that's also a tedious chore. So I think I'm going to just try to manage it the way it's given to us and just kind of scan through it one number at a time. So we're looking for numbers between 71 and 80. So I don't see any here in the top row. There's none between 71 and 80. Let's look at the second row, just kind of scan through there. I see some at the end, right? Barely, right? These barely fit in there, but we have 80. And I would recommend, if you have this on paper, if you've written these numbers down, somehow marking them off. So maybe this one I could have marked off already. 70, we've already counted that one. So that way we know we didn't miss any numbers. So if we get to the end and there's some numbers that we didn't mark off, we know, oh, we didn't actually count that number. We need to add it to our total. And also knowing that there's 107 values, we can double check at the end that we've accounted for all 107. So it looks like we have 3 here so far. So maybe I'll just kind of write a 3 out here to remind myself. Got one more here between 71 and 80. One more here. All right, that kind of misses the mark. So it looks like we have 2 in this row. Excuse me. There's another 80. Let me double check this one again. Okay, yeah, so Didn't miss any more there. Another 80, another 80, and another 80. So quite a few there. And again, it's easy to overlook if you're not being careful. So looks like we have 4 in that row. Making sure I didn't. So again, I check and double check and triple check just to make sure. And then the last row here, we have 1 more, right? And so if I add all those up, looks like we have 10. So we have 10 here in the 71 to 80 range. They're all 80s. And that is one drawback of the frequency distribution, is that once you convert the data values into that frequency distribution, you lose the original data set. So now I still have it here on my screen, but if I decide to construct this frequency distribution and then I share it with somebody without sharing the original data set, I just send them the frequency distribution, they would not know that all the values in this second group were all 80. All they would know is they're somewhere between 71 and 80. And so that would be the best that they could surmise, that there's 10 values somewhere between 71 and 80. And so again, like I said, you do lose some information when you convert your data set to a frequency distribution. All right, so we have 10 in this group. All right, so like I said, I'm going to pause it because these are going to take even more time to count up and the number's going to be a lot bigger. I'm going to pause the recording, and then when I resume, we should be right back at this table with the rest of the column filled out. All right, so just give me 1 second. Okay, so I finished going through the rest of the data set, and maybe you caught this the first time around, or maybe you caught it when you paused the video and tried to count out the numbers, but I missed an 80. So actually there's 11. So let's go back to the one I missed. It was right here in the middle somewhere. It was this one right here. I put a line through it. So I missed that one the first time around. So that's why it's really important, I think, even if you don't write these in numerical order, just to maybe write them down or have them printed out or something, and then mark them off as you're counting them. That way you don't omit one. Oh, it looks like I might have forgotten another one, but I think I have 107 now. That's okay. That might be a problem. I don't have this. Oh, I marked this one. When I paused it, there was the software I used to record had something in the way here. So I counted it. Now I remember. So make sure you mark every data value that you count. That'll help you catch any mistakes. I also experienced going through the 90 through, no, not that one. The 80 to 89, or sorry, the 81 to 90. That's what I did. I missed several 90s in this row. I don't know how I missed so many, but I think I missed those two and these two right here somehow. And so I had to add those 4 to my total. So my original count was 55, but there was 4 that I overlooked that I noticed when I did the last class. And so very easy to make those kind of mistakes. So you need to be very careful, very organized, double check, triple check to avoid making those same kind of mistakes. Now you might be saying, well, okay, that's fine, but I'm not going to have to do this, right? Yes, you are going to have to go through this kind of exercise in your homework on my stat lab. So there's a few problems where they give you a data set and they ask you to fill out a frequency distribution. And so, so be careful as you're doing that. You may want to use like a photo app where you open up the data. I don't know, I guess you'd be doing this on your computer, not on your phone, but you could also do it on your phone. You know, maybe take a picture of it on your phone of the whole data set, and then you can mark on it, right? So most phones have some way, I don't know, I'm not too savvy with cell phones, but where you could mark on the data as you're counting them. And maybe that'd save you from having to write out each number. And the last way to double check to make sure, so I've marked every number. I think I've counted them all, but a good way to double check is to see how many data values did you count in your frequency distribution to make sure it adds up to the number of data values in your data set. And to find the number of data values you've counted, all you have to do is add up all the frequencies. So if we add up this column, it should add up to 107. And so, and I think, and that's why I was kind of concerned, because I was like, oh, did I not count this 90? Because I did a quick check here to see that this would add up to 107. And if there's a number I didn't count, something wouldn't match up. And I was kind of worried about how I'd fix that. So thankfully, I'm sure I counted it, so I don't have to worry about that. And so this would be 10, and then 1 and 6 would be 7, and we'd carry the 1 over. And so we'd have I put it in the wrong place here, but 1, 2, and then 8 would be 10. So there's 107. Right, so if you add those numbers up, you do get 107. So that's a good way to double check that at least those numbers are matching up, and that should give you some assurance that you've counted everything correctly. And so here is our frequency distribution. And now that we've organized that data set into this frequency distribution, we do see that skewness, that the data is skewed toward the upper end, the 81 through 100. We see a lot of data values in those two groups, and we don't see as many on the lower end. So it's not a symmetric where there's a lot in the middle and a few on the outsides. It's most of them are on the high end, and there's just a few on the lower end. And so that's the distribution of the data. That's how the data is spread out among the possible values. So if we think of the possible values being between 61 and 70, we see the way the data is distributed among those values. And again, that it's skewed more to the high end. All right. So let's talk about some terminology of the structure of these frequency distributions. The upper class limit is the technical name that we give for the maximum value of a particular class. And the lower class limit is the name we give to the minimum value of a particular class. So these are pretty easy to identify. You'll have some homework problems where they give you a frequency distribution like this, and they'll say, what are the lower class limits? What are the upper class limits? And so you can just see them right on the table. These are the lower class limits right here. All right. So these are my lower class limits. So there's no calculation involved. You can just read these straight off the table. So 61 is the lower class limit of the first class. 71 is the lower class limit of the second class, so on and so forth. These are my upper class limits. And so on the homework, they're going to ask you to identify the lower class limits. So on the homework, you're going to say 61, 71. You just put them in a list like this. These are all my lower class limits. These are the minimum values for each class. Here are all my upper class limits. So 70, 80, 90, and 100. So 70 is the upper class limit for this particular class. 80 is the upper class limit for this particular class. On the homework, I'm pretty sure they will want you to list the values like this. So here are all the upper class limits for all the classes that I have. All right. And so that's that concept. So not too challenging, hopefully. It's a little more challenging with the next few things that we like to identify about our frequency distribution. And oftentimes you'll see this one given last, and that's the way I had it in my notes originally. But it's really helpful to identify this one first because it will help you with the other ones that we're going to be looking at, the other things that we're going to be analyzing about our frequency distribution. The class width of a frequency distribution is the difference between any two consecutive upper class limits or two consecutive lower class limits. All right. So the word consecutive there means in a row. So you have to take two classes in a row, two upper class limits in a row, or two lower class limits in a row. So I'm doing it like this, but really I should be doing lower class limits are over here, upper class limits are over here, right? The lower class limits are usually on the left-hand side of the class. The upper class limits are going to be on the right-hand side of the class. So you want two consecutive in a row. And you take the difference, which means you subtract. Right? So we want to subtract two consecutive upper class limits or two consecutive lower class limits, whichever calculation is going to be easier to do. And that's going to be your class width. And you don't have to check this with every pair of consecutive classes, because if it's a well-constructed frequency distribution, the class width should be the same throughout, right? We talked about that with this particular example, right? This is a bad frequency distribution because the class width isn't the same throughout. And so it's going to distort the distribution of the data when we look at this frequency distribution, right? Here, the class width would be 15, right? So the difference here between this lower class limit and this lower class limit is 15, whereas here it's 7. And so it's a poorly constructed frequency distribution. The class width should be the same throughout the entire frequency distribution for it to be a valid frequency distribution. So you should only have to do this calculation once, and you would get the same answer no matter where you do the calculation. All right, whoops, I'm going too far back. Okay, we want to go here. All right, so let's do the class width. And just to show you, we'll calculate it a couple times just to show you that it doesn't matter where the calculation is done. If it's a well-constructed frequency distribution, you get the same answer every time. So you want to take two consecutive upper class limits. So maybe we could take this one and this one. So consecutive means back to back or in a row or side by side, right? So we'll take these two and take the difference. So 100 minus 90 gives me a difference of 10. That is my class width for this frequency distribution. And I would get that value even if I calculated it somewhere else on the frequency distribution. So for instance, if we did it here, we'll take these two consecutive lower class limits. It's 71 minus 61, which again is 10. So it doesn't matter where you do the calculation. If you do it here, I don't know, I'm trying to think of where else we could do it. Here and here, 91 minus 81, again gives me 10. So the class width is uniform throughout the entire table, which is the way it should be. And so there's our class width, it's 10. All right. The most common mistake, now that I'm thinking about it, would be on the test. When students are asked to find the class width, if they haven't studied and are not careful, they will take the class width to be, and this, intuitively, this would seem to make sense. You would say, well, we have 70 and 61 here, so a lot of students would take 70 minus 61 and get a class width of 9. So they look at the upper and lower class limit of one particular class to get the class width, and that is incorrect. That does not give you the proper value. And 9 would be would make the rest of what we're about to do incorrect. So you'll see the value of calculating the class width in this way when we look at these next two things. All right, so that's class width. A class boundary in a frequency distribution is the value exactly halfway in between two consecutive classes. That means you want to look at the upper class limit of one class and the lower class limit of the next class and find the value that's exactly halfway in between those two. There is also a class boundary before the start of the frequency distribution and a class boundary after the end of the frequency distribution. So we kind of have boundaries on the ends of the frequency distribution and in between each consecutive pair of classes. All right. And so we will have a class boundary. This thing's getting kind of messy here, so I apologize for that. But there will be a class boundary between these two classes. So we're going to look for the boundaries here. And between these two and between these two. But then there's also going to be a boundary before the start of the whole frequency distribution and at the end of the entire frequency distribution. So we're going to have boundaries before and after the whole thing and in between all the classes. The boundary here for between the first two classes is the value that's exactly halfway in between 70 and 71. So you want to look at this value here and this value here and find the boundary being the value halfway in between these two. Now, oftentimes you'll be able to just look and intuit what that value is. So what's halfway between 70 and 71? It's 70.5, right? That's exactly halfway in between 70 and 71. So if the numbers are friendly enough, you can probably just figure it out by looking at it. However, the numbers aren't always friendly. So if this was like a decimal number, like 70.57, and this was 70.82 or something crazy like that, what's exactly halfway in between those two numbers? That's going to be harder to figure out just by looking at it. And so you'll want to be able to calculate it in those cases. And so it's a pretty easy formula for calculating. And I have it here at the end. So to find a number exactly halfway between two numbers, you simply take the average of those two numbers. To average those two numbers, you add them together and divide by 2. Right? That's how you take an average. You add up all your numbers, divide by the number of values that you're adding up. In this case, we're looking at two numbers, so we add those two numbers together, and since there's only two numbers, we divide by 2. And that's going to give you the value exactly halfway in between. All right, so let's go ahead and do that calculation here just to show that it works. So to find the value exactly halfway in between 70 and 71, we will average those numbers together. I'll take 70 plus 71 and divide it by 2. So 70 plus 71 is going to give me 141. Divide that by 2. You might need to use a calculator for that, but you will get 70.5. So we get that value there. All right. So 70.5 is the boundary between the first and the second class. What is the boundary between the second and the third class? To find that, we would want to look at the upper class limit of the second class, which is 80, and the lower class limit of the third class, of the next class, which is 81, and find the value exactly halfway in between those two. And that's going to give me the boundary between those two classes. Again, you can, by inspection, see that it will be 80.5. You could also calculate it this way, right? If we take 80 plus 81 and divide it by 2, we get 161 divided by 2, which is, again, 80.5. Excuse me, let me rewrite that. But there's an easier way, and this is where the class width comes in. The lower class limits are all spaced out at a distance equal to the class width, right? 61, the next lower class limit is 71. It's 10 away. The next lower class limit is 81, which is 10 away, et cetera, et cetera. Same for the upper class limits, right? So the first upper class limit is 70. The next upper class limit is 10 away, which is 80. The next upper class limit after that is 10 away, which is 90, et cetera, et cetera. The boundaries will follow the same pattern. They will be spaced out exactly the same way. So if the first class boundary is 70.5, the next one will be 10 away, which is 80.5, which is what we calculated over here. But what I'm telling you is that you can get that next class boundary without having to do another calculation. You just use the class width. So whatever the class width is, you add that to your first class boundary and it will get you your next class boundary. And so it's just an easier way of finding all the class boundaries. Instead of calculating each one separately, you calculate one of them and then you use the class width to find the rest of them. So the next class boundary will be 10 away from this, which is going to be 90.5. So those are the class boundaries in between each of the classes. But as I mentioned, we also consider a class boundary the value before the frequency distribution begins and after the frequency distribution ends. And the way we get to those is we just keep going. So I go one more time, I add the class width again, and I'm going to get 100.5 here. And that's going to be the boundary at the end of the frequency distribution. And then I go backwards to find the boundary at the beginning of the frequency distribution. So my first class boundary was 70.5. I want to roll that back to get the boundary at the beginning. So that means I will subtract 10. I'll go 10 before it, which will give me 60.5 here. And so these are all my class boundaries, and I'm sorry, it's a big mess. So maybe what I should do is list it out. Well, or maybe I could do this. I don't know. I'm trying to find a way where it's more visible on the screen. And I'm sorry, statistics is not my forte. It's not, my degree is in mathematics. Statistics is related to mathematics, but it's not exactly the same. And I've taught this class several times. I've gotten a lot better at teaching it and understanding the material. But as far as organizing the way I approach it, that has not improved at all. So I'm sorry, it's a giant mess. And there's several problems that we're going to encounter throughout the semester where there's just a lot of stuff going on, a lot of things you have to look at. And I just have not mastered the best way of organizing all that information. And maybe there isn't a way to master it. And this is just what everybody does. I really don't know. But probably be nicer if we listed it out here. So I'll go ahead and put the answers on these screens so it's just a little bit easier to see. So the upper class limits were 70, 80, 90, and 100. The lower class limits were 61, 71, 81, 91. The class width for our example was 10. And then our class boundaries were 60.5, 70.5, 80.5, 90.5, sorry, that's a point there, and 100.5. So these were all of our class boundaries that we found. All right, and then there's one more thing for us to calculate. So hopefully we can find some way to squeeze it on that screen, and then we'll put the answer over here. And this is called the class midpoint. A class midpoint in a frequency distribution is the value exactly halfway in between the lower and upper class limits of a given class. So it's the number exactly in the middle of a class. And again, sometimes you'll be able to just figure it out by looking at it. Other times you'll want to calculate it. And again, to calculate a value that's exactly halfway between two numbers, you take the average, just like we talked about here. Maybe. Okay. I feel like this thing's starting to kind of, lag on me. So hopefully, I don't know, I have a lot of screens this time, more than I usually do. Hopefully it doesn't freeze up or lock up on me. But to find a number exactly halfway in between two numbers, you take the average. So we're going to do the same thing for the midpoint. All right. But the numbers we're going to use here, instead of using the upper class limit of one class with the lower class limit of the next class, like we did for the boundary, we will take the lower and upper class limit of the same class and average them together to find the number exactly halfway in between. So maybe I'll write the midpoints over here. In this case, there are no midpoints before or after the frequency distribution. There's just a midpoint for each class. So we're going to have 4 midpoints for this frequency distribution. So we want the number exactly halfway in between 61 and 70. And for some students, they're pretty good at intuiting what that number is. I'm personally having a little bit of trouble intuiting that right now off the top of my head. So I'm going to go with the calculation method. So we're going to average these two numbers. If I want to know exactly what's halfway between 61 and 70, I will take an average of 61 and 70 by adding them together and dividing by 2. And that's going to tell me what's exactly halfway in between. And so this is going to give me 131 divided by 2. And so this will be 65.5. All right. So I'm pretty sure about that. So, 2 goes into 120 60 times. So that means 2 will go into 130 65 times. And then we're going to have that remainder of 1, which is going to give me that half. So that's kind of how I'm calculating that so quickly. And so we'll get 65.5 as our first class midpoint. And again, you do not have to calculate the class midpoint for each individual class. You can use the class width to generate the rest of the midpoints because the gap between the midpoints is the same as the class width. Every class midpoint will be 10 away from the previous one, right? So to get the next class midpoint, we will add the class width, which is 10, and that gives me 75.5. Now, I'm adding 10 because that's my class width. I hope you're not interpreting this to mean, oh, you always get the next one by just adding 10. It's going to be different for each problem because the class width will be different for each problem, right? So the number you want to add here is going to depend on your frequency distribution and what your class width is for that frequency distribution. I'm adding 10 because that's my class width. And, this is the luxury of being the teacher. You can kind of choose the examples you do to make the numbers a little bit nicer to work with. So I kind of chose these classes so that the class width would be 10 so that it was just an easier number to work with. But on your homework, you're not going to have that luxury. So your class width might be 7.5 or something horrible like that. If your class width is 7.5, then to get the next midpoint, you're going to have to add 7.5. And so you'll probably need to use a calculator to do that, right? So just whatever your class width is, that's what you're adding here. So I'm going to add 10 because that's my class width, and I get 85.5 for the next class midpoint. Add 10 again, I get 95.5. And so these are my midpoints for all my classes. So let's get back to that here. So we had 65.5, 75.5, 85.5, and 95.5. Now you might be saying, what is the point of calculating all these things? there actually is a use for these numbers that we're going to see later in the chapter. So not only is it something you're just going to have to do anyways because it's on your homework, but there is actually a use for the midpoints and the boundaries that we'll be seeing in 2.4. So we won't see it in 2.3, but well, kind of in 2.3 too, actually. We use the midpoints in 2.3 as well. So there is a use for this calculation. All right, so it appears I have 2 class midpoint slides. That's why I thought it was laggy, because it's there twice for some reason. I don't know, that's kind of weird. All right. We already talked about this, but I didn't know I had a slide for it. Consecutive class boundaries and midpoints have a distance between them equal to the class width. We already talked about that and used that fact to help us get our answers. This means you only have to calculate one. You can find the rest by successively adding or subtracting the class width, depending on which direction you need to go in. All right. The values of the class boundaries are numbers that cannot possibly occur in the data set. So sometimes I get students who feel bothered that when they look at their class boundary, which is 70.5, they'll say, but wait, that I don't see that number in my data set, so why is that okay to be the class boundary? For the boundary, it shouldn't be a number that can occur in your data set. If the class boundary is a number that can occur in your set of values, then it shouldn't be the boundary. It should be part of one of the classes so that it can get counted in the frequencies, right? So the boundary is in between the classes, and so data values should not, how do I want to say this? The class boundary should not be possible data values in your data set, right? But students seem to also be bothered that the midpoints can't possibly occur as part of their data set. So we saw in those Critic review scores, they were all whole numbers. 75.5 does not seem to be a possible Critic review score. They always use whole numbers instead. And so they'll say, but so you can't have a data value in our data set that equals the class midpoint. And that's okay. That's what I want to say is these midpoints and boundaries don't have to be values that can occur in the data set itself. All right. So don't let that bother you. All right. So where was I at? Right here. All right. So for the midpoints, I don't want to say that it can never happen. I think with midpoints, you can have some data values, some data sets where the data values in that set can actually equal the class midpoints, but it doesn't have to happen that way. So you don't have to, whatever your class midpoints happen to be, they don't have to be actual data values that have occurred in your data set. All right. So don't let that bother you. There are a couple of variations on this theme of frequency distribution that we want to talk about, but these are pretty easy to convert to. Once you have a frequency distribution, you can rewrite it as a relative frequency distribution. And all that is a frequency distribution with the frequencies replaced by percentages of the total number of data values. Right. So in a frequency distribution, you have the number of data values that occurred in that particular class, right? So we have 1 data value between 61 and 70. We have 11 data values between 71 and 80. We have 59 data values between 81 and 90. So in a frequency distribution, the frequencies here tell you how many data values occurred in each particular group. To convert this to a relative frequency distribution, you want to convert each of these frequencies into percentages. So we know the total number of data values was 107. So to convert these numbers into percents of the total number of data values, you take the frequency, which in this case was a 1, and you divide it by the total number of data values in the data set. And that's going to give you a decimal number, which you can then convert to a percent by either multiplying by 100 or just move the decimal to the right twice. So for me, when I think of percentages, I don't think multiply by 100. I feel like that's an unnecessary step to have to acknowledge, even though you do that. Because it's so easy once you have the decimal to think of it as a percent by just moving the decimal to the right twice. Then it's a percent. But that operation means you're multiplying by 100. So when I think of converting to a decimal, this is all I think of mathematically is take the number, divide it by the total, and then that becomes your percent. But it becomes your percent after you move the decimal place twice. All right. So let me see if I can pull up my calculator here, because I'm not going to be able to do this in my head. So here's my calculator, if it'll load up for me. Wow, my computer is going really slow for some reason. I actually have never seen this happen before. It's really not coming up for me. So let me try loading it up again. Okay, that was really strange. All right, and then we're going to calculate this percent. So we'll take 1 divided by 107, and we get this crazy percent, or not percent, we get this crazy decimal, which we can convert to a percent by moving the decimal place to the right twice. So we get 0.0093, we don't need the rest of these numbers really. Converting that to a percent, we're going to have 0.9345 blah, blah, blah percent. All right, so let me see if I can remember this. I'm just going to go to the 93, I think. So we have, this becomes 0.0093 as a decimal, and then that converts to a percent as 0.93%. Now, I'm probably just going to round this to the nearest whole number. I think that'd be okay for this exercise. So I'm just going to round that up to I was about to say 100%. I'm going to round it up to 1%, right? 0.93, we can just round that to 1, and this will be 1%. But it's actually a little bit less than 1%, right? And actually, because our number of data values is so close to 100, these are all going to be pretty close to the number that they already are. So maybe that's kind of bad. But 11 out of 107 is going to be close to 11%. 59 out of 107 is going to be close to 59%. And after we round, these might all actually just round to the numbers that they already are, which makes this a bad example as far as looking at the percentage version of this. So maybe I shouldn't round it. Let's keep these 2 decimal places just so they look a little bit different in our relative frequency distribution. So 0.93%. So that's what we will put way over here, right? So this is going to be relative frequency. So it's going to be 0.93%, right? 71 over 80. Let's look at that class. I went too far. So we'll do the same calculation. It's going to be 11 over 107. We'll bring up our calculator. So 11 divided by 107 gives me, so this one would have rounded down to 10. So it would have been different if we rounded. So maybe we can round after all, but let's not round for the moment. So this will be 10.28. Right. So again, as a decimal, this is going to be 0.1028. As a percent, this will be 10.28%. All right. So why don't you do the other two, convert these to percent. So pause the video, do that conversion, and then resume the video to see if you were able to convert to a percent correctly. And let's go ahead and keep 2 decimal places in the percent. And then when you resume the video, I'll skip the calculations and I'll just put the answers on the screen. So I'm going to pause my recording, do those calculations, and give you the results. Okay, so here are the values that you should have calculated for the next 2 classes. So for the 81 to 90 class, you should get 55.14%. And for the 91 to 100 class, you should be getting 33.64%. So we would have been okay if we rounded, because these don't exactly match those original numbers as closely as I thought they would. So, so this is our relative frequency distribution. Now you lose even more information here. So if you did not provide the data set or the original frequency distribution, but you just sent somebody the relative frequency distribution, they wouldn't know the original numbers in the data set, which is true of a frequency distribution as well, but they also wouldn't know how many numbers were in the data set either. This doesn't tell you how many, it doesn't let you know that we had 107 values. There might have only been 5 or something, right? And so with these percentages, you lose that information as well. But it also maybe gives you a better sense of the distribution of the data, right? So if we kind of look at these two, a good way to say this is that, 90% of our data was in the second 2 classes. 90% of our data was between 81 and 100. So it gives you an easy way of understanding the way the data was distributed and describing it, right? That's a nice way to describe the distribution of the data. 10% of our data was between 61 and 80, about 10%, and about 90% was between 81 and 100. And so, which means the Animal Crossing got good reviews, right? That game got pretty high marks overall, since 90% of the review scores were between 81 and 90, 90% of the review scores were between 81 and 100, which means that a lot of people, assuming 80 is a good score, 81 is a good score, it got high marks from 90% of the reviewers, right? And so we can maybe draw a conclusion about the quality of that game. All right, the last variation on a theme here is the cumulative frequency distribution, which is a frequency distribution with the frequencies replaced by the frequencies accumulated up to and including a given class. In other words, for each class, you add its frequency along with the frequencies of all classes that occurred before it. Sorry, I have a typo there. The occurred twice. So you're just adding up the frequencies as you go. So for the first class, it's going to look the same, right? How many frequencies do we have between 61 and 70? 1. And how many did we have before that? There wasn't any, right? This is the first class. So there's just going to be 1. So far we have 1 data value altogether, up to and including 70. For the second class, notice I changed the description here. We're not just going to be going from 71 to 80, but we're going to go all the way back to the beginning and add up all the frequencies that came before it. And so for the second class, what we will do, if we go all the way back here, the second class had 11 data values. So we're going to take those new 11 data values for the second class and add all the data values that came before it, which is just 1. And so now we have 12 altogether. So we're going to add both of these together and we have 12 accumulated frequency. All right. So we have 12 up to this point. For the third class, we will take the 55 new data values that we get from the third class and add it to all the data values that came before it, which would be the 12, right? And so we will have, whoops, I'm going the wrong direction. Yeah, we're not quite done. I'm sorry, this video took a lot longer than I thought it would. Usually, I feel like in class, this lesson goes pretty quickly, like, within, 30 minutes or so. So I don't know why it took so much longer on video. All right. So we have, I'm sorry, I said 55. That was the percent, right? That's where I got that number from. So we have 59 new data values in the third class, plus 11 plus 1. So we want to add all the previous data values as well. So we take all the new data values that we get from the third class, which is 59, plus all the data values that came before it. So we're going to add 11 plus 1, which will be 12 more to this 59. And so altogether, we're going to have, let's see, that'd be 60, 71. We'll have 71. All right. And then for the last class, we have, excuse me, let me go all the way back here. We have 36 new data values, and we're going to add to that all the data values that came before it. So we'll have 71 here plus 36 more, and that should add up to the total number of data values, which is 107. And so that's how you'll know that you've done this correctly, because the last frequency, the last cumulative frequency, should equal the total number of data values in your set, which is 107. And so this is useful for seeing how the data values grow as you go from the low end to the high end. And you can see here we have a huge jump from 12 to 71. All right. That also made me remember a good way of double checking here to make sure that this seems to be consistent and correct is that if you add up all the percentages, what should it add up to? It should add up close to 100%. Ideally, it should equal exactly 100%, but because we rounded to 2 decimal places in all of these, it might be something like 99.95 or something, but it should be really, really close to 100%. And that's how you'll know that it should give you some assurance that you've done these percentages correctly when you add them up. All right. So interpreting the data, a couple things you might want to look for. A normal distribution occurs when the data frequency peaks somewhere in the middle, is low before and after the peak, and is roughly symmetric, meaning it looks about the same to the left as it does to the right. So when I talked about skewing earlier in the video, it was in reference to a normal distribution. So a normal distribution is kind of what you would consider the typical distribution that you should expect. But if the data values occur more to the right or to the left, it gets skewed from this normal state. And so this is something you might want to be on the lookout for in your set of data. The data that we looked at in this video did not exhibit a normal distribution. It wasn't peaking in the middle and low on the ends. It was peaking more to the right. Now, if we divided our classes a little more granularly, where maybe we have the class width be like 2 or 3, you might get something that looks more like a normal distribution, but I still believe it would be skewed more to the upper end. As we saw, 90% of our data values were between 81 and 100. And so if that happens and it's more of your data values are to the upper end, it's not going to be a normal distribution. Normal distributions are very common and very important for later topics in the course. So this is just sort of a way of introducing the idea early, and we'll probably revisit it a couple more times as we go through the course until we actually really focus on it later. But we just kind of want to put the idea in your head at this point. But there are some homework questions I will ask you. Does this frequency distribution appear to be normal? Does it have a normal distribution to it? And I have an example where we can actually see that. A gap in the data or the occurrence of 2 peaks in frequency indicate that the data was collected from 2 different populations. For example, if we mix the Critic review scores for Animal Crossing with the player review scores, we might notice 2 different peaks in frequency, one for the critics and one for the players. Right, so this is the example that I really think of as a nerd that I am is Star Wars, the Last Jedi. So not the most recent one, not episode 9, but episode 8. Had very high critic review scores. The critics really liked that movie. I personally liked the movie, but the viewers, moviegoers, did not like it. So the average viewer was not happy with that movie and gave it a low score. So if we mix the 2 reviews together, the critics and the average moviegoer together, we would see 2 different peaks. We would see one peak where the critic scores occur, and we would see one peak where the moviegoers' scores occur. And so when you're looking at if we combined it all into one big set of data and we mapped it out and we saw that we have one big peak here at like 50% and one smaller peak over here at like 90%, we could intuit from that there's 2 different populations that were mixed together, the moviegoers and the critics, right? And so we could draw a conclusion based on that. All right. So here's a couple of examples from the homework. I'll try to do these quickly because this video is already an hour long. Identify the lower class limits, upper class limits, class width, class midpoints, and class boundaries for this frequency distribution. And here, I thought they'd make you type it in separated by commas, but they actually separate the values for you. So you just type one value into each box here. Also, identify the number of individuals included in the summary. And so we will get to that in just a second. Lower class limits are all in this column right here. So these are the lower class limits, which are often abbreviated LCL. So again, I'll try to speed through the end of this video to get over as quickly as possible. So 100, 200, 300, 400, 500. That's what you'd want to put here. I'm not going to write them all out, but I'll just write a couple so you get the idea. The upper class limits are these values here in this column. So these are the upper class limits, which I will abbreviate UCL, upper class limits. So those would be 199, 299, et cetera, for the upper class limits. The class width. So notice, it's kind of weird because like in the book, they do the class width last, but notice even in the homework, they ask you for this value now because it's useful for doing the next two problems. So to find the class width, so pause the video and see if you can calculate the class width, and then resume the video to see if you came up with the right idea. You shouldn't take you too long. So the class width you should find is 100, right? And it doesn't matter where you do that calculation, as long as you're using two consecutive lower class limits or two consecutive upper class limits. So I'm thinking these two. This looks like the easiest thing to do here. So here's two consecutive lower class limits. I subtract those. 200 minus 100 gives me 100. So there's my class width. I'm just going to put width here for that. For class midpoints, we want the value exactly halfway in between the lower class limit and the upper class limit of each class. So we'll start with the first class here. We have 100 and 199. I want the number exactly halfway in between those two. Again, you might be pretty good at figuring it out just by looking at it. I'm thinking it's 149.5, but I want to make sure. So I'm going to calculate it. And the way you calculate it is you average those two numbers together. Add them together, divide by 2. So we're going to get 299 divided by 2. We can use our calculator if necessary. 299 divided by 2 gives me 149.5. So my intuition on that was correct. So I get 149.5 for the midpoints. So we have, I guess let's do this here. We have the width here, which is going to be 100. The upper class limits here. The midpoints are going to start with 149.5, but we don't have to calculate the midpoint for the second class in the same way. We can just use the class width. We just add the class width to this number to get the next class midpoint. So I'm going to add 100 to this. So let's add 100 here. And that's going to give me my next class midpoint, which will be 249.5. So again, I mean, I said I chose my example in the video so that the class width was an easy number. It was 10, but they're doing that in the homework for you as well. So, and then add 100 again gives me 349.5. That's the next class midpoint. Add 100 again, we get 449.5. And add 100 again, we get 549.5. And that's where we stop because we see that's the last class. If we added 100 again, we'd get 649. There's no class for those particular values. So that's the end of that. And then the last thing we want to do are the boundaries. So again, we'll do one calculation and get the rest of them by using the class width. To find the class boundary, we want the value that's exactly halfway in between the upper class limit of one class and the lower class limit of the next class. We want to look at these two numbers here. So we have 200 and 199. We'll average those together, divide by 2. And that's going to give me 399 divided by 2, which is going to give you 199.5 when you calculate that, which is maybe, again, something you could figure out just by looking at it. And that's fine if that's what you want to do on the homework and the test. So 199.5 is my first class boundary. I'm going to rewrite that here, and you'll see why in just a second. And then I add 100 to get my next class boundary, so it'll be 299.5. Add 100 to get my next class boundary, 399.5. Add 100 to get the next one, 499.5. And then remember, there's also a boundary before the frequency distribution begins and after the frequency distribution ends. So to get the boundary at the end, we just add 100 one more time. So we're at this boundary here. To get to the very end of the frequency distribution, you add 100 again. We get 599.5, and so that takes me to just after 599. So that's the boundary at the end of the frequency distribution. And then to find the boundary before, at the start of the frequency distribution, we subtract 100 here, and we get back to 99.5. Now, sometimes if we start at 0 and you subtract backwards to get that original beginning boundary, it might be negative. I've had examples where I get something like negative 0.5 here. So that can happen as well in some data sets. All right, and so those are all your class boundaries. The last question it asks on this problem is, identify the number of individuals included in this summary, and to find the total number of data values, which is what that's really asking, you add up the frequencies. So we have 24 plus 92 plus 30 plus 2. And so that's going to be 8, right? 4 plus 2 plus 2 is 8. and then we'll have 12, 14, it looks like 148. And that's going to be the total number of individuals included in the summary. A very common way of indicating, I should have used this earlier in the video, but the letter, like in algebra, we use X as our variable. That's the common go-to letter for a variable. Well, in statistics, N is the common go-to letter to represent the number of data values. So we'd say N is equal to 148 here. And that means that's the total number of data values. All right, I have one more example. This one's a quick one. And this is kind of related to the next example we're going to look at. This also is not a normal distribution. This one's actually skewed lower, right? It's skewed to the left, to the lower end. So we see most of our data values over here at the low end, not so many at the high end. That does not look like a normal distribution over this spread of numbers. What does look like a normal distribution is what we see here. All right, so I wanted to do at least one example where we appear to have a normal distribution. Now, for whatever reason, they chop this table up into two different parts, which kind of bugs me. But if we join them back together, we would have 7 here, and then 4, and then 1. And if you look at this distribution of numbers, there's a peak in the middle of 12, and then it slowly lowers as you go either down or up from there. And it does so in a very symmetric way. It's not perfectly symmetric, but you notice this is a 7 here and this is a 7 here. That's exactly symmetric. This one's a 4 and that one's a 2. So there can be blips like this, but then these are both 1s. So that's highly symmetric. It's not perfect, but it's highly symmetric. So there's a peak in the middle. It's low on the ends and it's fairly symmetric in its distribution. And so that is what a normal distribution will look like. All right. And so here we're given some options to answer this question, because that's what the question is. Is this a normal distribution? The answer is yes, but they don't want to make it that easy on you. They don't want it to be like a 50-50 shot. So you have I guess it's still a 50-50 shot. If you know the answer is yes, it's going to be one of these two. But if you're just randomly guessing, it's going to be a 25% shot at getting it right. And that's probability. And we're going to be actually talking about that in a later chapter as well. So we have to read these carefully. Yes, because now only one of these is going to describe the normal distribution correctly. So we want to pick the one that describes what a normal distribution is. So you kind of have to know the definition. Because the frequencies start low, proceed to 1 or 2 high frequencies, then decrease to a low frequency, and the distribution is approximately symmetric. That sounds pretty good. I'm really tempted to say that's the one, but we should probably compare it to the other one just to see which one seems to be the most correct. So this one says yes as well, because the frequencies start low. That sounds good. Proceed to 1 or 2 high frequencies, then increase to a maximum. That is not what that's not what a normal distribution is supposed to do. It's supposed to decrease again on the other side. And the distribution is not symmetric. Also, not what we want to see in a normal distribution. So C has some issues with its description. B seems to be the most correct. And so we choose B. All right, so that concludes the video on section 2.1. I will see you in the next video for section 2.2.